who's going to give us an insight into how galaxies form and evolve. I hope that you really enjoy the event, and please give a warm welcome to Alfredo.
Okay, hi, my name is Alfredo. I am an astrophysicist and a science journalist. And my expertise is galaxy collisions. I wanted to be an astrophysicist since I was 12 and managed to do that. And what I want to do tonight is try to convince you why galaxies are just incredible. And so I'm taking you on a journey from the very beginning of the universe until the far future of our solar system. Galaxies are the link between the relatively small of us and planets and stars and the largest structure in the universe and the universe itself. And so I hope you will forget about being drenched in the rain and you enjoy smashing galaxies. So, I mentioned that we need to start from the beginning, but actually I want to put some limitation to our physics. I love science and assume that you love science too if you're here. But our science is not almighty and all-powerful, it has limitation. We keep pushing those boundaries, but there are boundaries there. We need to understand where they are and why they're there. So, people often ask me, oh, okay, you're an astrophysicist, what happened before the Big Bang? And we don't know. No idea whatsoever. I have a hypothesis, and I think that we could be part of a multiverse of universes that are very similar to our own, but it's based on a gut instinct. It could be anything. It could be nothing before us. It could be a universe that always been there, always will be. It could be knowns. There's no thing, we don't know what it is, so there is no point in asking the question. Well, there is point asking the question, we just cannot provide the answer. But it tells us that physics is limited. So we start from what we know, the Big Bang. And already, you don't start from point zero. You start from an instant after the Big Bang. Exactly 10 to the minus 37 seconds, which means is at 0.360 and a 1. In that fraction of an instant, that is when our physics began. Before that, we cannot use any of our physics. Our physics is way too limited to comprehend exactly what happened at time t equals 0. So, what happens there? You have the universe in a singularity. What is a singularity? It's a point of infinite density. Now, if a point of infinite density is fine, okay, I can imagine that I take a lot of mass or a lot of energy and I shrink it down to a single point. And I'm going to tell you that that point of infinite density is actually infinite in what we could comprehend as space-time. And I think you're just like, okay, that doesn't make any sense. Don't worry, because it doesn't make any sense to anyone on the planet. We can do with maths. With maths, oh, it's simple. We can see numbers that looks like, or symbols that look like infinity, but we are not meant to understand or comprehend this concept of infinity. So we usually skip that part and say, okay, 10 to the minus 37 seconds, something needs to happen. And that something is called the cosmic inflation. The universe expands billions and billions and billions of time in something close to 10 to the minus 36 seconds. So another tiny fraction of a second that we cannot understand. And suddenly the universe is much, much bigger. And a lot of things is happening as the universe expands. From the infinite energy, stuff begins to bubble up, and the things that we see in the universe starts to form, but very, very slowly. The first thing that happens is that the forces in the universe break apart. There are 4 fundamental forces. We have gravity, things fall down. We have electromagnetism, is what keeps magnets on fridge and compasses pointing towards the north. And there are 2 other forces that you might not be familiar with. One is called the weak nuclear force, which is important for nuclear decays. So in nuclear power station, it's fundamental. And the other one, it's very, very, very important, although we don't seem to experience it, and it's called the strong nuclear force. It keeps the nuclei of all the atoms together. So inside every atom, there are protons and neutrons, and there's tiny little particles inside those protons and neutrons that are called quarks. And the strong nuclear force is like a glue that keeps them all together. And in fact, there is a particle that sends this force from one particle to the other that is called a gluon, because physicists in the 70s didn't really have much fantasy, so we had stuff called gluons, and we have flavors particles that we're going to discuss that in a minute. So we have now the forces are separated, but what else is happening in the universe? We have that the first quarks begin to form, but they're still interacting too much with the strong nuclear force, and so you have a plasma. A plasma is a hot state, a hot, very, very dense state, and this is called quark-gluon plasma. And the reason why it's important is that now we have the technology to sort of test and to explore this quark-gluon plasma. And what's happening at CERN at the moment is studying this peculiar state of matter. So far, nothing that we have seen or experienced is out there. It's a big, hot, dense mess, the universe at the time. But as time passes, the universe begins to expand, and as it expands, it cools down. The closest analogy I can think of is a deodorant can. When you spray the deodorant, the can becomes cool. Why? Because suddenly there is less pressure inside, because there is less gas, so the molecules of the deodorant need to take a longer journey to hit the walls. So less pressure, and suddenly it cools down because you're taking away energy from inside the can. And that's exactly the same happening to the universe, is expanding, and some of the energy of the photons, the particle of light that were produced at the very beginning, are being stretched out and they lose energy. About 370,000 years after the Big Bang, something happened, something incredible. Suddenly the photons were cool enough to let all the other particles interact without any barrier. And something happened. Suddenly the light was free to move, and the universe became transparent. And the light is something that is still detectable today. We cannot see it, it's in microwave, but it's something called the cosmic microwave background. This is the echo of the Big Bang. This is the first light that shone in the universe. And it's absolutely wonderful, and I'll explain why it's wonderful. I mentioned that the universe expanded very, very quickly at the beginning. And that expansion is a little bit like sound waves. There were some turbulence because when something is very tiny, needs to obey to the laws of quantum mechanics. So it's laws of quantum mechanics leave a lot of leeway on what things should be and on the speed at which they're moving. And those tiny fluctuations, they form in a gigantic way in the universe. Now, the cosmic microwave background is incredibly uniform. If you consider that at temperature, it's almost the same, and it's about 2.7 degrees Kelvin, so minus 130 degrees Celsius. And if you see the bluest area and the reddest area, the difference between the two is 1/10,000 of a degree Celsius or Kelvin. So it's incredibly uniform, but you see, the area in red are places in which galaxies will form and had formed, and the areas in blue are what we call cosmic voids. And suddenly you have this, sorry, the other way around. The blue are the area of the galaxy, the red are the cosmic voids. And what you have is suddenly you can see where everywhere in the universe was going to be, and it is now. Thanks to the first light in the universe, there was already a path decided for everything in the universe. And The discovery of the cosmic microwave background is probably one of my favorite stories in astronomy, because although it's been taught for many, many years there should be this signal, this was the first proof that the Big Bang happened, that the universe was indeed expanding, astronomers could not find it. Their calculations were a little bit off. But there were two physicists that were working at Bell Lab in the States. It's a telecom company. And what they were doing, they were trying to get rid of all the noise from their antennas. And they tried everything, but it was all this residual noise. And they got very desperate, and they thought that it was bird droppings. So for an entire winter, they had to scrape bird poop of these giant antennas, and yet the noise was still there. And so they thought, okay, we need to work out where the noise is coming from. And the noise was coming not from Earth, not from the antenna, it was coming from everywhere in the universe. Every direction they looked, there was the same noise, always looking the same. And they managed to work out that it was actually of astrophysical origin. They looked into it and they realized that they discovered the cosmic microwave background. And they won a Nobel Prize for it, which proves that you need to go through a lot of crap to win the Nobel Prize. Okay, so I sort of skim on an important bit. How can galaxy, mention that the photons were so energetic that they were moving around and push the gas apart. So how can already in cosmic microwave background we have the shape of the future galaxies? It's because not everything in the universe is affected by photons, can be, and that means not everything in the universe can be seen. Actually, everything you have ever seen or you ever see, all the people, the Earth, stars, the moon, cows, anything is just 4% of the energy content of the universe. Everything. 26%, which makes about 85% of the matter content of the universe, is something that we call dark matter. We don't know what dark matter is, hence the name dark. And we know its effect. We know that it holds the galaxy together, keep them the nice shape that we're going to see in a minute. And we think there's some sort of particles that doesn't interact, but we haven't found those particles yet. There are some ideas that could be some primordial black holes that surround all the galaxy, but we haven't found any evidence of that either. So the moment is just dark matter. And in 1998, we realized there was something else in the universe that was even weirder. We found out for about almost 6 years that the universe was expanding, but there was this idea that the expansion would at some point stop and the universe will collapse back onto itself. It was called the Big Crunch. So at some point the universe would be slow down and collapse again. And we realized the universe wasn't slowing down, actually quite the opposite. The universe was accelerating. And the further a galaxy was from us, the faster, the more acceleration it had. And so we realized there was something in the universe that was pushing that acceleration. And we call that dark energy. And if we thought that dark matter was mysterious, dark energy is even more mysterious. But it's important to realize there are stuff in a universe that we cannot understand. But it's important. That's why we do science. We want to know more. We want to see more. And even stuff that are complex and weird, we're still very, very curious about it. So now we need to go back to, we introduced all the characters of our play, so we need to go back to getting to the galaxies. What happened at the beginning of the universe? We said that there is the light from the cosmic microwave background. The universe continued to expand, so the gas in the universe is free from the interaction with the photons, interaction with light, so it starts to cool down. And by cooling down, it starts collapsing on itself. And that leads us to the first stars. It's a bit counterintuitive to think that to have a star, a very, very hot star, you need to have very, very cold gas. But you just need to think that it's a little bit like gas is condensing, a bit like dew in the morning. It's just, it needs to cool down and shrink fast enough to explode into a star. And that's exactly what happens. You have a cloud of gas and it starts shrinking, and as it shrinks, it heats up the core fast enough to produce nuclear fusion, and suddenly a beautiful white bluish star is born. The first stars were incredible. We never observed one, so it's just mostly speculation, but we think that they could reach a mass of at least 1,000 solar masses, so 1,000 times the mass of the sun, or some theories says 10,000. Why is that? Because the gas, it was mostly hydrogen, so it was so pure that it had no way to cool down quickly enough. So the stars need to be so big to be able to collapse on themselves under their own weight. And when those stars explode, they will form very, very, very big black holes. And those black holes will eventually form the core of the first galaxy. So this is why it's important to mention the first stars. Hopefully by 2018, when the new space telescope is going to go online, we're going to actually observe the first stars, and we're going to find out if our theoretical prediction about them are correct. We know that there must be something that is very, very big because we found something last year. And what we found last year is gravitational waves. The discovery was announced in February, you might have heard of it, and it was a collision between two very big black holes. They're not supermassive black holes, they're not billions of times the mass of the sun, no. One was 29 and one was 36, so still big, but not incredibly big black holes. But in the universe today, you cannot form a black hole that big just by collapsing a star. So something else must have formed those black holes. And what we think that something else is the first stars in the universe. And as we learn in February, we know that gravitational waves exist thanks to the link between the two black holes. And that is not just proof that gravitational wave exists, that the technology to observe gravitational wave works, but also that these first stars must have been there. We have the first stars, we have the core of the first galaxies. We can go and talk about the first galaxies. So you can see this is a beautiful example of one of the first galaxies in the universe. This is actually probably the first spiral galaxy. And you can see that, as I mentioned, is pretty much whitish and blue. Why? Because the stars there are really young, really massive, really bright, and those are the color of hot young stars. If something is blue in the universe, it means hot, young, and means there is full of life. Life in terms of stars, not aliens. And this is fantastic. How does we have the core, we have these supermassive black holes, or a big black hole that is increasing. We have all population, 3 stars, not here, but is starting there. How does it get to a shape like this? It's all thanks to angular momentum. The things that keep your bike straight when you're pedaling is the same things that create the shape of galaxies. You start with a bigger cloud of gas. It's starting and starts spinning due to interaction with our galaxy, and eventually you form a beautiful spiral like that. So it's time to introduce our protagonists. And our protagonists are the galaxies. We divide galaxies in a lot of different ways, and I'm going to mention 2 because I'm so used to switch between all of them that you might want to have all the names if you need to follow me. These are the early type galaxies. They're either lenticular, means that they have a little bit of a disk, or they're elliptical, which they're big balls of stars. Although this looks like a fuzzy cloud, there is just a lot of individual stars all going around the center of the galaxy, but all going around a certain orbit and all different for all the stars. Here instead, most of the galaxy follow a disk. You can see there is a little bit of dust there. It means that the galaxy are not, there might be a little bit of star formation, but usually early type galaxies are old, they're yellow or reddish, and they have no new stars. So these are the galaxy towards the most aged galaxies. And then we have the late type galaxies. We have spirals, we have bar spiral, and the Milky Way is actually a bar spiral. We know that thanks to dynamical, we cannot see the bar from our place in the Milky Way, but we can see the effect of the bar. And then we have irregular, which are just very messy galaxies which are formed during flybys between galaxies, when two galaxies pass next to each other. So, a little bit of history of these galaxies. You see, they were only discovered about 80 years ago. Before we called them nebulae. Why nebulae? Because they look like fuzzy patches in the sky. Hubble realized that some of those patches had a specific shape, so he started thinking maybe there's something special about this object, but this is actually one of the pictures that he took of an elliptical galaxy, and you can't really tell much, but he had a tool that allowed him to realize how big the universe was. He managed to work out that these objects were beyond the Milky Way, and it was a revolutionary concept. At the time, astronomers thought the universe was static. It's always been there, was always going to be there, and nothing ever changed. And the universe was just the Milky Way. There were no ideas that the Milky Way had a certain shape. They know there was direction towards the core of the Milky Way that had more stars, but they just thought there was a big distribution of stars, and we were towards the outskirts. No idea about the spiral or anything else. No idea that there was things beyond. And then Henrietta Swan-Leavitt happened. She was part of a group of women called the Harvard Computers. They were incredible. They classified by naked eye, over 100,000 spectrum of stars. They were able to tell how hot and sometimes how massive a star was. But what she did, and it's her there in the background, she realized that certain stars have always the same luminosity. So they always shine with the same energy. That was a fantastic, incredible discovery, because she realized that you can use some stars as standard candles. It's like you have a 100 watt light bulb. If you have it on 1 meter, it's going to be, you're going to get a certain brightness into your eyes. 10 meters, the brightness is going to be less, but you can calculate the distance based if you know that it's 100 watts. And what she realized is that we can do that for stars, and she managed to measure the distance of the Large Magellanic Cloud, which is a galaxy that is visible in the southern hemisphere, and it's one of the tiny satellites that surround the Milky Way. And using those standard candles, she allowed Hubble to work out the distance of hundreds of galaxies and work out how big the universe actually was. But Hubble not only worked that out, also realized something, that the shape of the galaxy could mean that there was an evolutionary sequence. You see, in the 1920s, finally, the public and all the scientists were accepting theory of evolution, and they were fascinating and trying to find evolution everywhere, not just in biology, but in every single aspect of science, because it was something that was very compelling. It was something that was, at the time, became very, very clear to the public, and it was quite simple. You just need to take Darwin's ideas and just apply it to your field. And so we thought that at first there were ellipticals, and over time the ellipticals would steal gas from intergalactic space, start spinning, become lenticular, and then either becoming normal spirals or bar spirals. It didn't really mention irregulars because obviously irregulars would make a big problem in theory, so we ignore things that don't work out in science. It's brilliant because we saw it a few slides ago. That was a big fuzzy thing, and it managed to think, okay, maybe there is a connection between all these shapes. Because the question was, why there is variety? Why there is such a difference in the universe? Where does that difference come from? And it was almost right. There is an evolutionary sequence in the universe, but it goes the other way around. So, galaxy evolution takes our blue, young, full of gas, spiral galaxies, and over time turns them into old, red, yellowish, elliptical galaxies. And what happens is that every galaxy in the universe, over its lifetime, will have collision, interaction with other galaxies that will change their shape, that will first sometimes activate more star formation, sometimes devoid them of new stars, and turn them from this to that. And this is what galaxy mergers, this is what my PhD has been about, understanding the steps going from this one to that one. So these are three beautiful examples of galaxy mergers. This is the antenna galaxy, and you can see there are two spiral galaxies that are colliding. They're colliding on a plane, so it's probably not, although it's a major merger, so there are two galaxies more or less the same size, so you expect to be a very, very messy interaction. Like a star's going to be flung out of the galaxies. The fact that they're on the same plane, probably they're not going to create an elliptical galaxy, but a lot of stuff is going on here. Every blue dots around this galaxy, unfortunately it's not super brilliant, but the picture, but every blue dots, especially you can see them here and here, those are brand new stars, probably at most 10 million years old. Everything that is red, and you can see these huge patches, those are stellar nurseries. In those, and they're probably 100 or probably 1,000 of light years in size, 100,000 stars are being born as we see them. And they're just shining, they're so hot, and because they're very, very young, that they are making the hydrogen gas that form them into a big glowing red mess. And this is what we call the major merger. Two big galaxies forming, interacting. Usually the major merger is what turns galaxies into ellipticals. But we have stuff that is called minor merger, which it might seem a lot calmer. In fact, you see here the spiral is completely disrupted. Here the spiral is still there, and that's the notorious whirlpool galaxy, because it's a perfect whirlpool. But here there is a dwarf galaxy, and you can see that the blue stars and the big red dots are also in this galaxy. I think, okay, I can understand here. You have a lot of stuff going on. The gravity of the two big galaxies are pushing the gas together, they're compressing it, you're forming new stars. But here you think, this is quite tiny compared to this one. Why is creating this much star formation? It's because the big galaxy is actually eating the small one. We call it galactic cannibalism. It's just literally sucking the gas from the tiny galaxy and forming new stars. But fascinatingly, the small galaxy is doing something else as well. As the new star form, at the core of this galaxy there is a supermassive black hole, and it became active, and we call it an active galactic nuclei, or AGN for short, and it's pushing and heating the gas, so it's stopping a lot of new stars to form here. And finally, as example of galaxy merger, example of how galaxy change and form, it's the flyby, the things that form irregulars. And this is called the penguin galaxy. as you can see, is an adorable penguin. It's my favorite galaxy in the whole wide universe. But this one that it should represent the egg of the penguin is actually a much, much bigger elliptical galaxy that passed by and completely turned a nice spiral galaxy, as we saw before, into this weird mess. This is the core of the galaxy, and you see that, so this one is probably 30,000 light years in diameter, and suddenly this arm is being stretched out to probably something close to 200 light years, so about twice the size of the Milky Way. So, what happens in detail during galaxy mergers? The first step is rejuvenation process. This is again the antenna galaxy, but now we're looking at them in infrared. Infrared allows to peer through the cloud of gas because you're looking at the heat. And you see, so we saw before that the antenna galaxy quite dusty and it's quite bright, but suddenly you look at infrared and the entire galaxy is shining because star formation is not just on the visible patches that show, it's everywhere in the galaxy. When two galaxies merge, you have a lot of new stars. It's simply because the tidal forces, so the gravity between these two galaxies, exerts such pull and push on the gas that just create compression waves, and suddenly, bam, you have a lot of new stars. And you go in a phase that turns your normal spiral in star factories. The Milky Way is, in every sense, an average galaxy and produces one star the mass of the sun every year. During a merger, galaxies are capable of producing hundreds or thousands of stars the mass of the sun every year. But that production comes with a cost. Though most of those stars are very big, and stars that are very big, they go through their fuels very quickly. And what happens is you form a lot of, there was another thing. This is another galaxy, this is post-merger. So you see, this one is after the big merger happened, and you see there is a lot of star formation inside. This galaxy is called NGC 4889, and you can see a lot of spots of hot red gas, but you see a lot of dark feature is not as bright as when the galaxy was merging, or merging here. It's stuff had gone on. So what went on? After a while, the big early star died because they consumed their fuel very, very quickly, and they turned into supernovas. So you have this, the first become red giants and then collapse on themselves. And after they collapse on themselves, they produce large clouds of gas. So this process is what produces all the heavy elements that makes us. Produce the carbon and the oxygen, the iron, the uranium, everything that we can physically touch was made in a star. And usually this process is just continuous because you form this gas cloud, you push that gas cloud, the beginning is very hot, but then it cools down and form new stars. And from those new stars, from new stars, new planets, those new stars will go supernova again and form other new stars. But in a galaxy merger, that process is cut short. There's something that's called a feedback mechanism. I kept hinting that there are these supermassive black holes at the center of galaxies. And although they're fine, we have one, a very big one, is 4 million times the mass of the sun, center of the Milky Way, but it's very nice, it's very friendly, hasn't done anything bad to us. But there are some that they become so active that they completely destroy star formation in galaxies. They produce this feedback mechanism. They heat up the gas so quickly around themselves and then push this gas out that create galaxy-wide winds that warm up the gas to a point that the gas cannot cool down anymore to form stars. And quite a good example is this one. So that is an elliptical galaxy, slightly bigger than the Milky Way. So the Milky Way is across 10,000 light years. I think that is 150,000 light years across. And these big red lobes are actually radio detection of the gas emitted by the radio jets emitted by the supermassive black holes. So it's just the supermassive black holes that is producing these high energy particles and is heating up the intergalactic gas to something about between 2 and 4 million degrees. And from one end to the other, that is 4 million light years. So you see a tiny galaxy, and the supermassive black holes at the center is probably only a few light years in size, and create something like this. So you can understand how the supermassive black holes, when it is activated, can completely heat up a galaxy and kill all the star formation. So we have now an idea for a galactic life cycle. What you have is galaxies that are born in the early universe, and over the lifetime they're going to interact, and when they interact, form new stars, and eventually activate their supermassive black holes and turn into something that is a little bit elliptical. Understanding this life cycle, it's important because, as I said, the galaxy connect the solar system is us, to the full structure of the universe. And it might seem quite far removed. We think, oh, how is it connected to us? You said the Milky Way is such an average galaxy. It is, but the Milky Way has also been quite noted in the past. We have the Large Magellanic Cloud that I mentioned earlier. Henrietta Swan-Leavitt measured its distance, and you see it seems like a big mess, but it's actually a bar spiral, like we think the Milky Way is. Here's the bar, this is one arm, and this is the second arm. The problem is it's been disrupted, and there is the Small Magellanic Cloud, which is another galaxy that orbits quite close, and go around the Milky Way, and the Milky Way is so big that it stretched apart and created this mess. But there is also something else that has that the Milky Way has connected to mergers, and it's something called the Sagittarius stream. So if this is our Milky Way, we see some stars, not as many, here in what we call the halo of the Milky Way, and there shouldn't be stars there. And the reason why there are stars there is because probably there was a tiny galaxy that was eaten by the Milky Way. But to get a little bit apocalyptic, there's also another reason to care about galaxy mergers, and this is where I drive my point home, is the fact that we are all going to be killed by Andromeda. Eventually. Andromeda is the closest, largest galaxy to the Milky Way. It's 2 million light years away from us, and it's slightly bigger than the Milky Way. And Andromeda is coming, but technically we're moving closer to Andromeda. But it means that in about a billion years, Andromeda and the Milky Way will start merging, and we're going to turn it into an elliptical galaxy. So I have a little bit of what is the view going to be like for us. They made simulation, quite accurate simulation, and 87% chance that the sun will not be affected by the merger. Simply because the merger is such a slow process that it takes billions of years, so nothing is really going to happen. The sun is going to change its orbit around the Milky Way Andromeda galaxy, but nothing really bad is going to happen. 10% is going to be hit by supernova waves, or a lot of new stars are formed nearby and completely destroy the solar system, and there is 3% that it would be flung out of the new galaxy. But this is the... No? All right. This is what it looks like. So this is London with no lights and a dragon. The Milky Way, and that's Andromeda approaching. 500 billion years in the future. 100 billion years in the future, London is gone. And Andromeda starts interacting. we see new star being born, and suddenly the arms are spread, and we see the cores that start getting closer and closer together. Things get a lot messier with more supernovas, and eventually the two supermassive black holes are going to be active and are going to be interacting, more supernovas, and eventually it will become an elliptical galaxy. And this is what we're going to be seeing in the night sky. No more a nice band of stars, but a big ball. And this takes me towards the end of my talk. I hope that leads to that there is such a variety of galaxies because there is an evolution in the universe. And we have a menagerie of galaxies. We have galaxies that are so different from each other as you and me. We have a thin galaxy or thick galaxy. We have blue galaxy, red galaxy, yellow galaxies. Regular, irregular, and complete mess. The galaxies make us understand our place in the universe. They make us understand that everything in the universe, from the infinity big of the universe itself, up to the problems that we face today, it's all connected. And we can see that there is a beginning, a middle, and an end for everything. But galaxies are lucky because they just need a tiny new little galaxy around them, and suddenly they can steal a little bit of gas and suddenly turns younger again. And we cannot do that, but maybe we'll find a way. And for now, we can just look up and enjoy the amazing variety that we see in the universe. Thank you. I'm happy to answer some questions. So if you have any questions, I can't really see you, so